today to invite Dr. Karen Troy from the Worcester Polytechnic Institute for our invite session today on orthopedics. Dr. Karen Troy is interested in musculoskeletal health and structure and physical activity and biomechanics, and that really also is the subject of today's talk, where she's going to talk about sticks and stones may break my bones, but exercise should be helpful, right? Just a quick reminder, Karen and I are also co-organizing a symposium later in the day after the coffee break in the same room here on quantitative image-based biomechanics, so you're invited to that as well. Like all other invited talks, this one is also 3 hours long. No, I'm joking. Just to check if you're awake. It's 40 minutes, and we're going to have a nice question and answer after that. So, Karen, please.
Okay, good morning, and thank you for the nice introduction and also for the opportunity to present some of this work. Before I move on, I wanted to make sure I put a bunch of other contributors in my cover slide here, because if I forget to acknowledge people along the way, I wanted to make sure that I acknowledge them now. So lots of people contributed to the work that you're going to see here, and they all probably deserve more credit than I do. So I wanted to start by talking about a couple of important people in my life. So this is my daughter, Claire. So she's 11 years old right now. She does a lot of different types of physical activities. Some of them involve quite high impact, and she's not remotely thinking about her bone health. But I think about her bone health because this is what I get to study. And when I think about what I want for her, I really want to be able to maximize her peak bone mass so that I can reduce her lifetime risk of fractures. So on the flip side, here's my mom, right? So she actually, I should update my slide. She turned 72 yesterday, and she's another person who does some types of mechanical loading. So she's interested in, she's a runner. She's got some risk factors though, which have actually led to her having a hip fracture this past winter, which I'm unhappy about. But anyway, she's doing great. And the point is she's also a runner, and she's another person who's interested in using different types of exercise. And so in both cases here, exercise is a part of their lifestyle, and it could be helpful for bone health. And at different ages, we have different priorities and needs, and our ability to influence our bone can also be different. So we know that mechanical stimuli make bone bigger and stronger. If you watched Dr. Mueller's talk yesterday, you probably got most of my introduction slides already. But here's a great example of racket sports players. You can see that the racket arm is much larger in the bone compared to the non-racket arm. We know some very classical experiments using turkey ulna have shown that mechanical loading can lead to bone formation, whereas when you take away the load, you actually see bone resorption. And so all of these different types of loads we know can make a difference. And this has led to a general paradigm that we have of functional adaptation in bone structure. And the idea is that most of the time our bone is in equilibrium, and so whatever mechanical stimuli we're experiencing during our lifetime is resulting in no net formation or resorption once we're skeletally mature. But of course, once you add some sort of novel mechanical stimulus, you're going to get a hypertrophic response, so you're going to get the addition of bone, whereas if you take, whoops, going backwards, whereas if you take away the mechanical stimulus, then you're going to see an atrophy response, and you're going to see the loss of bone. And we can talk about a little bit about what that stimulus is. There are a number of different mechanisms that probably all work concurrently, but the point that I wanted to make here is that all of these are either directly or indirectly related to some sort of measure of mechanical strain. And so when I move forward in this talk, I'm going to be talking about mechanical strain as the primary driver, even though, of course, it's much more complicated than that. So a couple of examples. So when we think about atrophy, a spinal cord injury is actually a great example of this, where you're walking around normally one day, you become spinal cord injured, now you're paralyzed, and you've now stopped loading your bone. And so a number of years ago, Brent Edwards and Tom Schnitzer and I looked at mechanical strength in the proximal femur of people who had recently become spinal cord injured, and you can see that the baseline and the follow-up, the bone strength decreases pretty much universally and really quite dramatically in most individuals. On the other hand, there's a lot of work looking at athletes and hypertrophy. So this is sort of an older but classic paper by Christine Snow looking at gymnasts and bone mineral density. And what you can see on the x-axis is time with the blocks indicating the competitive season. And then on the y-axis, you've got lumbar spine bone mineral density. And you can see that over the competitive season, gymnasts are gaining density, and then they lose a little bit during their off season, and then they continue to gain. So this is a great example of how exercise can actually increase bone. We know from animal loading models that there are certain characteristics of the mechanical signal that seem to influence osteogenic response. So some of the mouse tibia loading models have shown us that strain magnitude seems to make a difference. And so when you compress on a mouse tibia, you can see that there's an increase in cortical area that is added that is proportional to the amount of strain that's being applied. And we also know that strain rate makes a difference. And so in this case, again, mouse tibia, the black bars are indicating the loaded limb, the gray bars are indicating the contralateral limb. And you can see that the high strain rate groups had greater bone formation rates than the low strain rate groups. So we know that strain rate and strain magnitude seem to be two characteristics of the mechanical signal that are important for adaptive response. So I'm not the first person to ask the question, what if we could design exercises to be osteogenic? And what if we could identify people most likely to respond to exercises based on biomechanics or biological factors? And so there are a number of these different equations and relationships that have been proposed to try and predict osteogenic response. And what you can see in a lot of these is that there are several things in common. So most of these have some component indicating magnitude. So in this case here, there's some strain. This again has strain. There's a frequency component or an acceleration component. In many cases, so again, ground reaction force, a lot of them include something like the law of diminishing returns. So they've got either an exponential relationship or a logarithmic relationship that basically say that once you get beyond a certain point, perhaps your bone isn't paying attention. What they all have in common, too, is that they're not accounting for necessarily for individual differences in bone structure, or they're a little bit nebulous. Maybe they haven't been validated prospectively in people. And so when I try and think about what I'm going to tell my mother to do, I can't really figure out how to use these equations, right? I don't know if they're valid in people. I don't know which strain or which acceleration or which frequency to use. So theory is great, but I'm really a little bit more interested in reality. So what I'm going to do is discuss a couple of different techniques that we use, and then I'll show you some examples of how we've tried to tease out these relationships in people. Because we're using people, we actually are a little bit limited in the techniques. We can't put their arms into mechanical testing machines and break them, so we have to get a little bit more clever about how we measure stuff. So the first thing I'm going to talk about is some quantitative image analysis, and then we'll get on to how we actually understand bone loading in vivo. So I think it's helpful to think about what makes the bone strong, and we think about this really in terms of macrostructure, microstructural stuff, and then the material itself. And collectively, all of these different aspects are going to contribute to bone strength. And here I would define bone strength as literally how much force or torque does it take to break the bone. And so we can measure many of these things indirectly by using quantitative CT. And the way that this works, so what you're looking at now is an image of like a forearm here. So this is sort of distal radius and ulna, and then this is the first carpal row up here on the top. So the concept is that the X-ray attenuation value, which is basically the gray value you see, when you take a calibrated image, is going to be proportional to the amount of mineral that's present at that particular location. And so what you can then do is you can identify the voxels that you're interested in, and you can start adding them up and doing math with them. And so you can calculate things like you can calculate bone volume within a particular region, bone mineral density, you can calculate the bone mineral content, and then you can also do some calculations to calculate moment of area or even section modulus. So by selecting voxels in very specific regions, we can actually make some pretty good calculations that are quite precise and quite repeatable. So now we have a way to measure stuff about bone, but we really want to understand how the structure behaves. And bone structure is quite complex, as you just saw, and so to do that, we use finite element models. And you've probably seen a lot of rainbow pictures in your life, but if you're not a modeler, you may not actually understand how those pictures get generated. So this is my 10,000-foot view, which is that bone is really a complex structure, and so what we can do is basically discretize it into many thousands of very simple structures. So in this case here, we've taken an entire distal radius, and we've divided it up into tens of thousands of very small tetrahedrons that are all connected together. And each little tetrahedron is quite a simple math problem, and so once we know how stiff that tetrahedron is and how it's connected to its neighbors, we can now predict the mechanical behavior of a more complex structure. So we have to validate our models to make sure that they're actually going to give us good and accurate predictions for whatever parameter we're interested in. So this is an example of the type of validation that we would do in the lab. So in this case here, we take the anatomy from CT data. So this is a specimen-specific model. And from that, we're going to get things like the bone size and the shape and the density. And based on that information, we can assign both the shape of the model, the geometry, and also the material properties of the model. Then we have to assign it boundary conditions. So this is basically the loading magnitude, the direction, the rate, and whatever surface interactions there are. So when you lean on your hand, you're actually loading your carpal row, and then the load gets transmitted through to the radius. Then we take the same bone, we make a model of it, so you see an example of what the model looks like here, and then we can, and in this case here you see we've put strain gauges on the distal radius, and then we can compare our measured strains to our predicted strains to see how well we're doing. And so after we have tweaked the model so that we get good predictions, now we can go forward and we can make models based on images without having to actually strain gauge a person. So if we know what the boundary conditions are, we can now predict how the bone is going to behave in vivo. So the next trick then is we have to understand what are those boundary conditions, and those can get quite complicated. So we have a general approach to estimating in vivo bone loading conditions, which is not too different from some of the others that you may have seen at this meeting if you've gone to some of the sessions. The first thing we do is identify structures that are interacting with our bones of interest. So in this particular example, you can see distal tibia, but of course when you walk or run, the load is really transmitted through the talus up to the tibia. So we have to include both of those. And then you can see there's actually also a cartilage layer here. If we were modeling more of the tibia, we would also have to include the muscles that are being attached. The next thing is that we need to understand what are the forces being applied. So if we're looking at gait, for example, we might be measuring kinematics and kinetics to get the forces that are being applied at the foot. And then from that, we're going to have to calculate joint contact forces. And then once we've got those contact forces, we can apply them as forces and constraints to our model. So here again is our distal tibia. Here's now our axial and shear contact forces at the joint, and then those get applied to the talus and then are going to get transmitted up through the tibia in this case. Okay, so a couple of examples. The first one is really trying to explore the paradigm of whether strain magnitude and strain rate actually affect bone adaptation in healthy adults the way that we think it should. And so it's really looking at how valid this model seems to be prospectively when we look at real people doing a real activity. So this was a prospective randomized trial. We had 102 healthy adult women that participated in a voluntary distal radius loading experiment for a 12-month period of time. And we divided them into 5 roughly equal groups. So we had a high and a low strain magnitude group, a high and a low strain rate group, and then a control group who continued normal activities without changing. So the study design looked like this. So basically it was this 12-month prospective study. Our hypothesis based on the animal literature was that the high strain rate and the high strain magnitude groups would gain more bone than the low strain rate and magnitude groups. So this is a distal radius loading task. Basically it's the human equivalent as much as we could get of sort of a mouse tibia loading model. So again, we can't put people into a materials testing machine, but you can ask them to voluntarily do tasks, and we can give them different instructions on how to do those tasks. So in this case here, they've got a little load cell. It's attached to a data logger, so we can actually record what they did. And then there's the 2 LEDs that will light up when they hit a target force that we can set. And so all of the subjects were given one of these little loading devices, and they were sent home. And then we did CT scans at baseline and at 12 months. We also did high-resolution peripheral quantitative CT at 3-month intervals, and you can see the different groups here. So one of the things that was pretty unique about this study is that we were able to actually assign strains, not just forces, like you might do in a typical exercise study. So for each of the groups, we had a target strain or a strain rate, and then we were able to create a subject-specific finite element model for every individual participant. And with that participant, we were able to determine a force versus strain relationship based on their individual anatomy. And based on that, then we assigned to that person a target force, which we programmed into the loading device. And then with that loading device also recorded what the subject actually achieved during their voluntary loading sessions. And then we were able to plug that back into their finite element model so that we were able to create, then understand what they actually did. So we know what we told them to do, and then we actually know what they did. And now we can look at both of those things. So a little bit about our subjects. So I'm going to sort of walk you through this chart here. So these are our 5 different groups across the top. We have our low and high strain magnitude groups on the left, the low and high strain rate groups on the right, and then the control group on the far right. You can see that they're all quite similar in terms of age and height and body mass, so there was no difference between those groups. If we look at the low versus the high strain magnitude groups, you can see that the strain magnitudes were about twice as large in the high strain magnitude groups as the low. And I'm happy to go into what the source of those slightly different numbers are, but not now because it's complicated. But anyway, the point is the high strain magnitude group was assigned more strain than the low was. Similarly, the high strain rate group was assigned a strain rate that we anticipated to be about 10 times the strain rate of the low strain rate group. And this was actually done based on instruction set to the subjects. So they were either told to load their forearm slowly and evenly, or giving it a little impact bump, which based on our preliminary data would be very quick. So then we can look at what we actually told them to do. So everybody was told to load with a target of 4 days per week. Our goal was really to have them load at least 3 days per week. This is what they actually did, and so you can see it's pretty all over the map. We had subjects who were extremely compliant. We had subjects who didn't do anything at all, and pretty much everything in between. This is their, again, sort of what the prescribed strain magnitude versus the achieved strain magnitude was. And my main point here is that we did get a range of achieved strain magnitudes. Again, you can see the standard deviations are quite large, but it was quite all over the map. And in many cases, subjects were not able to achieve the strain magnitude that we had originally prescribed them, partly because if their wrists started to ache, then of course we had to back off, right? So people, again, are not rats. And then same thing with the strain rate. You can see, again, a range, but not nearly as large of a range as we had hoped. Finally, we tried to get at loading dose a little bit, and even though there are all of these very complex relationships that I showed you a bunch of equations for earlier, we just started out with a linear combination looking at strain rate, strain magnitude, and then the number of times that the subject had actually completed the loading intervention, just to get a measure of compliance so that we could sort of understand what the total dose was. So this is actually showing us baseline data now from the cohort. So on the x-axis we have distal radius. This is actually aerial bone mineral density, so it's a DEXA measure. On the y-axis you have energy equivalent strain for an arbitrary 300 Newton load. So this is from the modeling data now. And basically this is going to give us sort of an inverse measure of stiffness, right? If your bone is stiffer, you're going to have low strain for an arbitrary load, whereas if your bone is less stiff, you'll have high strain for an arbitrary load. And I hope what you can appreciate is that the scatter is very big within the subjects, so that even the amount of variation that we had within this very sort of homogeneous, healthy group of women aged 21 to 40, there's quite a lot of scatter. The one take-home that I'll point out from this is that a 1 standard deviation increase in bone mineral density, which is not a lot, resulted in about a 20% increase in bone stiffness, and probably about the same amount of increase in fracture strength. So even the normal variation is quite large in bone strength. When we look at the prospective changes, this is the percent change in variables. So this is integral BMC. So this is basically bone mineral content inside the periosteal surface, and then a couple of subregions. So inner bone mineral density within the trabecular region, and then bone mineral content just inside the cortex. What you can see is that the control group generally loses a little bit of bone. The low and the high strain magnitude groups really didn't change at all, and the low and the high strain rate groups all had significant increases in these measures. So that was not really what we were expecting. When we started to look at dose a little bit, we had a hypothesis that there would be a dose response. So this graph now shows all of our subjects that completed the data that are sort of collapsed together. We calculated the dose of what they actually achieved, and then we looked at their total change. So this is one example where we now have the strain dose on the x-axis, and this is now percent change in this inner trabecular region on the y-axis. And what you can see, of course, is that the data is quite scattered, but there is a significant and quite strong relationship between dose and percent change, even though it only explains about 12% of the variance. So I started to get a little worried that maybe there was something going on between our groups, and maybe there were some demographics that were different. And so what I did next was I divided the subjects into tertiles by the amount of bone mineral content that they gained or lost. Okay, and so when we look at if we just take all of the subjects who finished the study and we divide them into either gain or losing bone, the group that gained the most bone gained about 3.8% bone mineral content, whereas the group that lost bone on average lost about 2% of their bone mineral content. And I wanted to just understand what's different about these groups. Maybe there's something that's different about people who respond to mechanical loads versus those who don't respond to mechanical loads. And reassuringly, the only things that were actually different between these groups had to do with the loading intervention. So we found that the loading dose, the peak force, and the loading rate were all significantly higher in the group that gained bone compared to the group that lost bone. So I think that's a pretty reassuring indication that the loading is actually what's making the difference here. So our overall hypothesis for this study had been that strain magnitude and rate drive bone formation, and we did find that loading dose was consistently related to the change in bone, but only explained a very small amount of the variation. We also found that the baseline data showed a huge amount of scatter, but the key take home here, I think, is that a 1 standard deviation increase in bone mineral density really resulted in quite a significant increase in bone stiffness. And this probably doesn't mean a whole lot, but the subjects who gained the most bone really didn't have to do that much. So on average, they completed 130 loading bouts over the 1-year period, which is less than we had prescribed, and they had a mean strains and strain rates which were not exceptionally high. And so I think that's a good take home, which is that it may not actually take that much to gain bone, and we worry about that, especially when we're thinking about joint injury with this type of a loading activity or any type of an impact load. So it may not actually be that onerous to do this. And of course, there's all sorts of limitations to the study. The main one that I want to bring up right now is this issue that we really had to deal with a lot of very pragmatic concerns about making sure that subjects were safe, dealing with compliance, and so in theory and reality are not quite matching up here. So partway through, so the next thing I'm going to talk about is bone adaptation in marathon training. And before I forget, this is my little reminder. So my master's student, Tomo, is actually presenting more detail about this work during the Journal of Biomechanics Awards session. And even though Pinaki just gave a plug for the session that we are presenting in this room, this one is competing with our session. So now you have 2 great choices for the 10:30 session, so you can go see whichever one you want. So partway through doing this distal radius loading experiment, which was a ton of work, I got really frustrated because I kept telling people what to do, and sometimes they would do it and sometimes they wouldn't. And I thought, you know, what I should really do is find an activity where people are intrinsically self-motivated to do it, right? Something that you really want to do, right? And then I thought, you know, a few years ago, my mom asked me to run a marathon with her. And I said, that's a terrible idea, right? Like, who wants to run a marathon? But there are very few excuses you can give your mom. So if your mom ever asks you this, right, you can't tell her you're too old or too tired or, you know, too anything really. Instead, you just kind of say, okay, I guess we'll go do that, right? But then as I was thinking about this experience, I thought, you know, when we were training for that marathon, we had a lot of intrinsic motivation, right? We were keeping training logs, and I had my little spreadsheet. I still have a little spreadsheet, right, with like a graph of the mileage and all of this stuff, right? And it's a pretty structured training program. So we thought that maybe marathon training, and especially for naive runners, would be an activity that would be really physiologically relevant, but would also be something where now we're looking at really a steady increase in bone loading, and it would be an opportunity to think about it as a model system for looking at bone adaptation. And the other thing about running is that we know that running can be both beneficial and harmful. So in theory, although you could add mechanical load and have a stronger bone, we also know that there's a high rate of injuries and potentially risk for stress fracture. So we could ask then, is marathon training actually good for bone? So this is what the study design then looked like, and this is a little bit abbreviated, but I'm going to call your attention to this box down in the lower right-hand corner first. So we enrolled runners who had already volunteered, who had already registered for a first marathon. They had never run more than a half marathon in their life, and they also hadn't had more than about 4 weeks of 20-mile-per-week runs over the last 5 years. Okay, so they were not high-mileage runners when they started, but for some reason they had all said, gee, I'm going to run a first marathon, and they'd signed up. So we enrolled them, and then we also got an age and sex group, matched group of non-runners. So for the runners, which is what I'm mostly going to focus on, we got a CT data of their distal tibia. We collected running biomechanics. We collected high-resolution CT to measure microstructure, and then we followed them over their training period. And so we didn't tell them what to do, but they kept training logs, and they gave us that information. And then at some point, most of them were able to successfully complete their marathon, and then within a month after that, we brought them back for a second follow-up CT scan. And I did want to make sure, since I seem to have forgotten to acknowledge all of my other collaborators, and I apologize. This work was performed by I can't even pronounce his real name, but we call him Tomo, who's presenting at the J Biomechanics session. And then also Becky Fellon from USARIUM and Jessica Ventura from Gordon College helped with this project. So again, we use our general process for measuring, for estimating in vivo distal tibia strain. So we've got our biomechanics of running, which was then used to do inverse dynamics calculation. Based on that, we were able to make an assumption about what was happening at the joint. This was a fairly simplified model, and in this case, we were really just looking at the instant of peak ground reaction force as a starting point. And so from that, of course, we can estimate our joint contact forces and then apply them directly to our model as boundary conditions. So the next thing we needed to do was think about how we were going to be quantifying longitudinal changes within the bone. And so we now have the distal tibia, and I'm really going to be focusing just on this slice here, which we take with the high-resolution PQCT. So we divided it into quadrants, which you can see here, and then we also divided it into cortical and trabecular regions. And so we had a couple of hypotheses that we were looking at. One was that runners would experience a change, and the second thing was that that change would be related in some way to strain or strain gradient or something, right? So again, we had prospective data. We were simulating the running biomechanics before they started ramping up their miles, and then we were looking at change over time, pre and post. So here's sort of the basic results of the study. So 11 of our 15 runners actually completed the marathon training. 9 of them actually finished their race. We did have one who didn't start, who was sick on race day, one who didn't finish for another reason. In total, those who actually completed the training ran about 600 kilometers during their training period, over which was sort of 4 to 6 months. And in total, the runners had a 1.5% increase in cortical bone mineral density. But none of the other changes that we looked at the tibia were significant. So the bar graph here actually shows a snapshot at the baseline data of the runners compared to the non-running controls. And the main differences is that this D100 is really the total bone mineral density within the distal tibia, and then this D-trab is the trabecular density. And you can just see that the runners in general had a little bit better bone than the non-runners did. This image just gives you, again, a quick snapshot of 2 different runner and non-runner. So both are 40-year-old females. And if you look at this D-trab variable, this trabecular variable, hopefully what you can appreciate is that right in the center of this 40-year-old female non-runner, the image in the bottom, you can see that there's just a little bit less in there. So there's just a little bit less bone, and that's what that decrease in trabecular density is showing us. So we were able to make really cool pictures, right? I love these rainbow pictures. So we were able to calculate strain gradients and a lot of other different metrics. Again, one of the challenges that we're dealing with is we don't know what outcome measure to actually use when we're trying to move forward. And so I'm just showing you a snapshot of some of the different images to try and illustrate the fact that each of these measures, whether we're looking at energy equivalent strain, which is sort of a it's a general strain magnitude versus strain energy density versus the strain gradient, we're actually getting quite different information from each of these measures. And so when we start to try and look and see what's driving local bone adaptation, we tried out a couple of these to figure out what was going to work best. So this is, again, sort of a summary of some of the basic changes. In the boxes here, you see total bone mineral density, and then you see the bone mineral density for cortical and trabecular. At baseline, these are the values for the running group, and they were all significantly higher than the non-runners. And then you can see the change over time, and the only one that actually changed was cortical bone mineral density, which increased for the runners and actually was slightly different for a slight decrease for the non-runners. On the graph here, we can see now, this is the compressive force on the tibia at the instant of maximum ground reaction force on the x-axis, and then we see change in a particular variable on the y-axis. And the blue line here, which is sloping down, shows us cortical area, okay? And so what you can see is that the higher your peak ground reaction force, the more you're losing cortical area. Whereas the higher the peak ground reaction force, the more you're gaining trabecular area. So what this tells us is that at the undosteal surface, right at the inside of that cortex, that bone is actually getting converted from cortical bone to trabecular bone in people who have very high peak ground reaction forces. Whereas if you have a low peak ground reaction force, it's actually going the other way, okay? So yeah, we'll go there. Okay, so the next thing is showing us strain gradients. And do you guys actually see my mouse? You don't even see my mouse when do you see this? Okay. Do I have no, well, anyway, it doesn't work. You know what? I'm not even going to go there. It's good. I'll just keep waving my hands. It's all good. Anyway, okay. So if you look at the graph on the left, so this is showing a strain gradient on the x-axis, and then it shows us change in cortical bone mineral density on the y-axis. And now we're looking at the 4 different quadrants. Okay. So each individual subject has 4 data points, and again, hopefully, what you can appreciate is that everybody's sort of sloping down. And so what that's telling us is that the higher strain gradients are associated with decreases in cortical density. If you look on the the right-hand graph, you can now see strain gradient on the x-axis and changes in cortical volume on the right axis, the vertical axis. And again, you see they're generally sloping up. Again, lots of scatter, lots of variations between individuals, but this relationship was significant. And so what we were able to show is that increases in cortical volume, and the way that we've measured it is we can actually interpret this increased cortical volume to be periosteal bone apposition. So the bone is getting bigger as a result of having larger strain gradients. So just a quick summary. So we know that our runners experienced some mild changes during marathon training. They had increases in cortical bone mineral density. We also know that relatively lower ground reaction forces at peak seem to be more beneficial than having very high forces. And we know that high strain gradients are associated with periosteal expansion. But we also see that there is a ton of variability between people. And again, this was a pretty wide age group and mixed sex group. One comment that sort of occurred to us afterwards is that for distance running in particular, there's a lot of loading cycles, and then there's also what happens during each individual loading cycle. And so if we think about this law of diminishing returns, it's entirely possible that the number of loading cycles is maybe going to be contributing to damage, whereas maybe the first 100 or first 1,000 loading cycles is what's really contributing to adaptation. So if we go back to some of the original questions I asked, do mechanical stimuli actually related to strain actually drive bone adaptation in people, and can we measure it? So my answer is yes, but it's maybe a lot more complicated than we thought. And these are the first studies that I'm aware of that have prospectively related bone strain and adaptation in people. One of the things I wanted to comment on over the course of this conference, and a lot of other meetings, I've seen a lot of people who have taken bone structures, for example, a proximal femur, and then based on an assumption that bone adapts, they have inferred what must the mechanical loads have been in order to cause this bone structure. So it's basically sort of going at it backwards. And I wonder if when we do that kind of an approach, if we're creating sort of a self-fulfilling prophecy. So I think it's important to be a little bit careful about that because we don't always know what bones are experiencing. But it does tell me we need to know a lot more about what bones are experiencing to really understand this problem better. And I think one of the other important questions, especially when we start thinking about exercise and physical activity, is to figure out where do we draw that line between an exercise or a mechanical load being beneficial to bone and improving bone strength versus actually resulting in injury. So if we go back to our original little loading paradigm here, we know that bone adaptation is quite complex. It involves the interaction of biochemistry and mechanics, and strain-related stimuli are really only part of the story. And of course, there's 10,000 other things, especially in people, that I didn't mention. And so I'll quote sort of the great philosopher Yogi Berra, who said, in theory, there is no difference between theory and practice, but in practice there is. And I think that's definitely the case for this particular problem. So if we think about revising maybe our model for mechanical stimuli and bone adaptation, we started off with our nice little atrophy and hypertrophy paradigm, and there's this cute little line. So I'm just going to make that line really fat. And I think trying to figure out what is responsible for this really large amount of scatter is going to be a really interesting problem for us to understand in the future. So if I go back to my mother, and I think about what should I tell my mother, having now spent years investigating this problem, I can tell her to keep exercising for a number of reasons, partly because it's going to keep her from falling, partly because it's going to be good for her bone health, and I can tell her to keep running, but she probably should run maybe with a little bit lower impact if she can, and probably all of the miles that she likes to do are really not actually going to be helpful to her. When I think about my daughter, I'm going to tell her to keep doing what she's doing, run fast, jump high, and then think really about prevention. And so I'm kind of we'll go back again. I go back to this one key finding, which is that if we can just move everybody, shift them one standard deviation further, I think that's going to make a huge impact during childhood for preventing lifelong fractures. So with that, I wanted to thank all of the people that have contributed to this work. I've highlighted in red everybody who was directly involved in these projects. So Megan did a lot of the distal radius loading work, as did Joshua Varn, Brent Edwards, and Tiffany Butler. Tomo did a lot of work on the marathon training study, as did Becky Fallon and Jessica Ventura. Tom Schnitzer worked on some of the spinal cord injury data that you saw here. So with that, I'm happy to answer any questions. Thanks.
Thank you very much for the talk, Karen. We could have questions. If you can please stand up and introduce yourself.
Hi, Kat Daniels from Sports Engineering in Alberta, University of Bristol. How strong is the relationship between the ground reaction force metrics and your tibia strain rate, strain metrics?
All right, so the question was, how strong is the relationship between the ground reaction force and then the tibia strain rate? There's quite a lot of scatter, and it really depends on individual anatomy, is the short answer. So I don't have the numbers off the top of my head. I mean, it's definitely a linear correlation, right? Bone, when you're loading it physiologically, it's going to behave fairly. But because there is so much anatomic variation in individual structures, the strain that you get at a particular location is going to be quite different from one person to the next. So I don't think I put it in here. And if you go to Tomo's talk, he actually presents the strain values. They all exceeded, within our simulation, they all exceeded 1,000 microstrain, which is sort of our threshold for thinking something might be osteogenic based on animal work. But it was quite variable. Yeah, so most of these subjects were running on roads. There were a couple that mixed in training, and I can't tell you any more detail than that because I don't remember it off the top of my head. I do know that in general, when we looked at like the vertical average, the instantaneous loading rates and some of those other measures, they were not super high impact runners for the most part. So these group of runners was a little bit older. I think the average age was close to 40. And they weren't really pounding it. Yes?
Isabel Sacco from University of São Paulo. Thank you for your clear and amazing talk. I was just wondering if, of course, there are differences in magnitude of load, but could you comment on the difference of your findings for the upper limb and lower limb?
Yeah, I think one of the questions that we had was lower limbs, of course, experience many habitual loads, and upper extremities in general, we don't think about experiencing many habitual loads. And so part of what we were hoping to get at eventually is to understand where is that threshold for when bone adaptation might occur versus something else. So I think in both of these cases, clearly the task was a more novel task, and that may be actually why we saw larger changes in general, because people don't generally, I mean, we do lots of activities with upper extremities, we push and we pull things, and maybe you do push-ups. In that particular subject group, we actually excluded people who had very high upper extremity loads, so anybody who was a softball player, anybody who was a gymnast, or we had one person who was a competitive CrossFitter, right? So some of these groups we actually screened because we expected that their habitual loading would be very different. And I think that's a really key thing. And I don't know exactly how it's going to play out, but generally I would expect that it will take more to get lower extremities to adapt, simply because you have to exceed the threshold of what's habitual already. Yeah.
And I know that it's very, very difficult, but I just wonder if you made any hypotheses or projections about their relative effect on stiffness and strength.
So that's a great question. So we had originally thought that both magnitude and rate matter, but based on the literature, we were thinking that rate might be a little bit more important. I do think I didn't really show that level of detail, but I do think there was some evidence that the rate mattered a little bit more. There's some issues in terms of compliance and some other things. So we actually calculated different dose metrics. One of them was only based on strain magnitude. One of them was only based on strain rate. Then we had this combination metric, which I showed you today. Almost all of those actually were significantly related to the change, but the strain rates, the ones that included strain rates, to do a little bit better than the ones that included strain magnitude only. Yeah.
Yes, please.
Yeah. Oh, okay.
Over there.
My name is Vandana, and I'm from Polytechnic University. I'm wondering if there is any relationship between high resolution developing CT result that we extracted from, for example, tibia as a peripheral skeleton to the axial skeleton used like femur, that we know that fracture of femur, especially for osteoporotic person, is crucial.
So you're asking about the relationship between the high-resolution PQCT measures at the distal tibia versus something like proximal femur strength. Yeah, so we do know that a lot of these measures are correlated quite significantly. They're sort of generalized skeletal health measures, and so there are many research studies looking at either distal radius or distal tibia, high-resolution CT microstructural parameters in particular, and they found that they're good predictors of fracture risk. They can help a little bit beyond the bone density measures, but because of course you're not looking at the same site, so they're another sort of generalized measure of skeletal structure. I think that's probably the best answer. Yeah.
Hi, Kevin Thomas from Stanford University.
Mm-hmm.
I was wondering if, in your upper body study, if the compliance number of times they ended up actually in the protocol, and then also in the marathon study, if you'd asked their mileage or step counts, and if you had looked at any of that data.
Yeah, so the compliance for the upper extremity loading, we actually tried to sort of bake into some of the measures that we looked at that got at loading dose. And so if I go back to the, let me flip back really quickly here. So if I go back to the graph that I just showed, this one, you can see that any subject who actually didn't do anything, we assigned a loading dose of 0 in this particular analysis. So that definitely mattered. With the marathon training group, we did keep track of mileage, and one of the things we'd like to do actually is start to include that in some of the analyses. So that hasn't really been included, and I think the other thing is that we haven't really calculated a loading dose metric for those marathon studies. That's a little bit of a newer analysis. Yeah.
Thank you.
Well, okay, we're out of time.
Yes.
All right, come talk to me afterwards.
For the interest of time, to close the session now. Let's thank Karen once again.